Welcome to part 2 of my playlist about the preparation of benzaldehydes. This video is again about electrophilic formulations, but this time of methylated arenes. Most examples are reactions of stoichiometrically methylated arenes with DMF or other formyl cation equivalents, but I'll also show you some examples of catalytic methylations. Unlike the reactions discussed in part 1 of this playlist, the reaction conditions here are usually strongly alkaline. One practical strategy for the generation of methylated arenes is halogen-metal exchange. This can be done with stoichiometric amounts of a metal, for instance magnesium or sodium, with stoichiometric quantities of organolithium or Grignard reagents, or with catalytic amounts of palladium-0 complexes. Reaction of these methylated arenes with a synthetic equivalent of a formyl cation then yields the target aldehyde. Typical electrophiles suitable for this purpose are formamides, formic acid esters, carbon monoxide, orthoformates, and isonitriles. Some arenes can also be methylated regioselectively by treatment with a strong base. For instance, aryl ethers, arenes with chelating groups, and halogenated arenes are particularly acidic and easy to methylate stoichiometrically with lithiated secondary amines or polar organometallics. Some polyhalogenated benzenes can even be deprotonated by potassium terzbutoxide. Potential side reactions of this strategy include the formation of secondary alcohols by reaction of the product with the methylated arene. Then, a number of base or metal-mediated reactions of the target aldehyde can also diminish its yield. Let's have a look at some specific examples. Grignard reagents can be prepared from aryl chlorides or bromides, either by treatment with metallic magnesium or with isopropyl magnesium chloride. If the reaction with metallic magnesium does not start, addition of a small amount of diisobutyl aluminum hydride often helps. In this example, a substituted aryl magnesium chloride was treated with 2 equivalents of DMF at room temperature, and a good yield of the target benzaldehyde was obtained. The reaction of polar organometallics with protons from water or alcohols is thousands of times faster than their addition to carbon electrophiles, such as DMF. Therefore, if a large excess of DMF is used to formulate a strongly basic organometallic reagent, the DMF should not contain any water or other protic solvents. I usually add some sodium hydride to the DMF prior to its addition to the nucleophile to convert all acidic protons into hydrogen. Grignard reagents containing leaving groups are inherently unstable and should be treated with care. Here, a 3-chlorophenyl magnesium chloride was sufficiently stable to enable its formation at 66 degrees Celsius. Reaction with just a slight excess of DMF yielded, after hydrolysis, the target benzaldehyde. Even sterically shielded aryl halides can be methylated with magnesium. In this example, no DMF, but N-methylformanilide was used as electrophile, which is slightly more electrophilic than DMF. The purification of the product, however, was less straightforward than with DMF. An even larger scope of aryl halides can be converted into Grignard reagents by treatment with isopropyl magnesium chloride instead of metallic magnesium. The methylation conditions are milder, what allows the preparation of inherently less stable Grignard reagents, for instance those containing cyano or alkoxycarbonyl groups. Here, such a cyano group containing Grignard reagent was converted into an aldehyde by reaction with N-formylpeperidine at 0 degrees Celsius. This is an example of one-pot procedure where phenyl magnesium bromide was used both to substitute 2 chlorine atoms and to generate an aryl magnesium halide intermediate. The final formulation was achieved by treatment with ethyl formate. Because of steric crowding, the yield of aldehyde was good and no substantial amounts of secondary alcohol were formed. With less sterically demanding Grignard reagents, however, reaction with ethyl formate usually gives high yields of symmetric secondary alcohols. Halogen-metal exchange of aryl halides with butyllithium already occurs at temperatures below -50 degrees Celsius. These reactions should be conducted at such low temperatures to prevent reaction of the lithiated arene with butyl chloride. At higher temperatures, butyl arenes will become the main product. In this example, the metallation could be conducted at -30°C. Polychloroarenes are strongly acidic, and the methylated arenes are therefore weak nucleophiles only. Nevertheless, a fair yield of benzaldehyde could be obtained here by reaction of the lithiated arene with DMF at -40°C for only 15 minutes. This is a rare example of methylation by substitution of a methoxy group with sodium. The resulting intermediate was probably stabilized by the two adjacent methoxy groups. Addition of this organosodium compound to an excess of N-methyl formaldehyde gave a low yield of the expected benzaldehyde. In this case, if the formaldehyde was added directly to the organosodium intermediate, no aldehyde but only a secondary alcohol was isolated. This may have been avoided by lowering the reaction temperature further and maybe by using more solvent if precipitation of the organosodium reagent prevented efficient stirring. I'll show you now some examples of arene methylations by deprotonation instead of halogen-metal exchange. It seems that 2,6-dialkoxyaryl sodium intermediates are particularly easy to generate. In this example, 1,3-dimethoxybenzene was methylated regioselectively at room temperature by treatment with metallic sodium and a slight excess of chlorooctane. Quenching with DMF and hydrolysis yielded the expected aldehyde. This strategy could also be applied to the methylation of other methoxybenzenes, thiophene and benzofurane. This is an example of the twofold methylation of 3-chlorobenzoic acid by lithiated tetramethylpeperidine. At -50°C, no elimination of chloride occurred, and the aldehyde was obtained by treatment with an excess of DMF. As mentioned, polyhaloarenes are acidic and can sometimes be deprotonated even by alkoxides. In this example, a regioselective stoichiometric lithiation was achieved with LDA as base. Interestingly, if the reaction was quenched with water instead of acid, the alkaline conditions quickly brought about a regeneration of the starting arene by nucleophilic deformylation. This shows that the arene in this case is a strong acid and its corresponding anion a good leaving group. In this example, twofold deprotonation of an acylated 4-aminopyridine succeeded with an excess of butylithium at 0°C. No migration of the pivalloyl group occurred. Treatment with a large excess of DMF and hydrolysis yielded the target aldehyde in high yield. Benzaldehydes can be orthomethylated with trimethylethylene as transient protecting group and an excess of butylithium. Treatment with DMF and hydrolysis then yielded phtalaldehydes. Aryl magnesium intermediates have also been prepared by methylation with magnesium amides, as shown here. No arenes were formed at 0°C, and the expected benzaldehyde was obtained in good yield. Let's move on to catalytic methylations, followed by electrophilic formulation. In this example, chlorobenzene was treated with carbon monoxide and an excess of sodium formate in the presence of only 1% of a palladium complex. After heating to 150°C for 20 hours, a high yield of benzaldehyde and some benzene were obtained. These reactions proceed by insertion of palladium-0 into the carbon-halogen bond, followed by insertion of a palladium-bound carbonyl group into the carbon-palladium bond, as sketched here. The sodium formate was required as hydride donor to reduce the intermediate acyl-palladium complex to the aldehyde. Instead of carbon monoxide, isoelectric isonitriles can also be used as formyl cation equivalents. Here, the reaction was conducted in DMSO at 120°C for 5 hours. Again, formate was the reducing agent. In this example, triethylsilane was used as reducing agent. Because of the higher reactivity of aryl bromides, if compared to chlorides, the formulation already proceeded at 90°C. To prevent acidification of the reaction mixture, one equivalent of sodium carbonate was also added. This additional base is not required with sodium or potassium formate as reducing agent. Instead of carbon monoxide or isonitriles, certain formic acid derivatives may also act as formyl cation equivalents. Here, N-formylsaccharin was the formulating electrophile. Formic anhydride is not sufficiently stable to allow isolation and storage at room temperature, but the mixed anhydride of formic and acetic acid can be prepared, purified by distillation and stored at 4 degrees Celsius. There is a procedure in organic synthesis. Because of its low stability, however, it is usually prepared just in time by adding formic acid to acetic anhydride. This anhydride may also serve as formyl cation equivalent for the palladium-catalyzed formulation of aryl halides, as shown here. No reduction or formulation of the acetyl group occurred. Aryl diazonium salts can sometimes also be used as electrophiles in palladium-catalyzed C-C bond-forming reactions. In this example, a diazonium tetrafluoroborate was formulated with carbon monoxide and triethylsilane. Alternatively, aryl diazonium salts can be formulated under Sandmeyer-like conditions by treatment with the oxime of formaldehyde and copper salts, as shown here. The yields of this procedure are low, however, and the complexity of the reaction is high. Let's check some potential side reactions. Methylated arenes containing leaving groups can decompose thermally when allowed to warm to a certain temperature. With leaving groups ortho to the methylation site, arenes are sometimes formed, which can dimerize, oligomerize, or react with an excess of methylating reagent, as in the example shown here. In this instance, only one major product was formed, but because of the high reactivity and low selectivity of arenes, this is not always the case. An excess of a reactive methylating reagent, such as butyl lithium, can cause the formation of many byproducts. In this example, twofold methylation occurred, and a fraction of the target aldehyde also reacted with the methylating reagent. First, a secondary alkoxide was formed, which, after elimination and vinylic methylation, was transformed into a substituted cinnamic aldehyde. These side reactions may have been avoided with a smaller excess of butyl lithium and by fast addition of pre-cooled DMF to the reaction mixture at a lower temperature. Here are some further references which you can also find in the description of this video. The next video of this playlist is about the oxidation of methyl arenes to benzaldehydes, either directly or by intermediate benzyl halides or benzylic dihalides. See you then.